Так, глянь.
По-моему, там так тут я.
Ты нашел кого спросить, конечно.
Кого нашел?
А? Ты смотри.
Сейчас.
Там в чате же объяснял. Я же не читал.
Так, нет, пока не началась. Сейчас схожу на третий.
А там есть вода и что-то. Там есть вода.
Ну да. Но когда у нас такая листовка, как не только константы, а есть, допустим, этот датчик, что вы
Если бы так решение предлагаешь, что уже освоили фундамент, да, то есть главный член вот этот, а тут вот этот. Поэтому предел очевидно изменится.
Хорошо. Ну вот я даже вынесла n, здесь 1 плюс 1 на n, на n у нас 0, здесь. Второй случай, то, что модуль p больше единицы. Соответственно, вот у меня вот то же самое, я делю на bv. Так получается
Questions you just need to solve this problem and that's all.
Значит, теперь мы докажем, что предел n делить на bv стремится к нулю. По признаку Даламбера возьмем вот этот ряд, он будет сходиться, мы в общем возьмем n плюс 1, поделим на b n плюс 1 и умножим на да, вот мы просто рассматриваем вот такой, чтобы потом здесь сказать, что это стремится к нулю. По признаку Даламбера возьмем вот это вот n плюс 1 поделим, допустим, x плюс 1 поделим на x. Вот здесь. Вот здесь вот считаем, вот здесь у нас сокращается, у нас получается n плюс 1 поделить на d, умноженное на n. Выносим вот здесь f, вот это сокращается. Рассказано, что
нужно найти,
значит, вот это будет значит, Ламбера сходится, а из того, что он сходится, следует, что ну, это необходимо признать ряда, следует то, что этот предел стремится к нулю. Соответственно, дальше я это использую, вот здесь это стремится к нулю, ну, это стремится к нулю тоже, потому что
я сама же знаю, что тебя не началось, а уже нажали,
то
да?
есть у нас плюс 1 он как бы...
Точно туда можно.
Стремится к нулю, вот тут стремится к нулю, значит, остается 1 делить на 2 стремится к нулю. Значит, мы доказали, что это было при модуль альфа меньше 2, это при модуль альфа.
Нет, пока нигде не вижу.
Случай,
Кто-нибудь видит вот на YouTube?
соответственно, альфа.
Ну ты да, я сейчас на ютубе
У
смотрю.
нас там только
Он есть.
А,
Туда пошел просто.
Кудинове, да.
Да,
Да,
работает,
Кудинове.
просто пошел в элементы мотора.
Она идет сейчас в слот Кудинова, в элементы Матлури.
Странно, так это... Нет, ну что...
Вот, это...
Запись идет просто
Да,
не туда.
это наш-
Критическая ситуация.
наш
Последняя.
трансляция.
Пошло в Кудин, ну, зашло.
Да, да.
Хорошо, ладно, тогда переименую, создам ему новый слот. Странно, потому что я же создавала, ну, показывала. Ну, короче, зашло туда, зашло.
Это-
Все сейчас тоже записалось, да?
Ну, да. Да.
Хорошо, я
Кто-нибудь в чат курса написать, что...
Сейчас я тебе переименую, как только поднимусь на...
Там кто-то может...
Ладно, все.
Да, я напишу, скину.
Кто-то спрашивает, будет трансляция. Спасибо. Так, okay, let's start. So, this lecture and the next lecture, possibly these are the most important lectures of the course, because we will talk about the ergodic theorem, which is the central theorem in the course. So let me introduce the following definition. Okay, first let me call this topic stationary measures. Is it visible? Yes.
Yes, but probably it's better to, yeah.
What do you mean? Okay, so I think that I should change that problem, right?
Возможно, просто надо сделать шрифт побольше.
No. Okay, so let me change the.
А вот мы можем приблизить страницу, на самом деле.
Слева карандаш нарисован.
Если вы продаж нарисован, но это не том. Размер здесь меняется, просто стоит максимальный. Вопрос можно.
Может, маркер?
Максимальный.
Да, можно страницу увеличить.
По-моему, маркером, по-моему, плохо получается, насколько я помню, да. Давайте, знаете что, я думаю, что в прошлый раз мы уже с этим сталкивались, и в прошлый раз это вот так решили. Сейчас. Здесь какая-то еще была пожарка.
Спуски, может.
Во, наверное, вот это, да? Не вроде бы получше. Оп. Нет, не там. Не так. Так, нет, это что-то не то, да? Сейчас. Вот, все, наверное, вот. Вот, все, вспомнил. О, точно. So now it's better, right?
Yes.
Okay. Stationary measures. So definition. Distribution P is called stationary if we take this distribution, we apply the transition probability matrix to the right, and we get again the distribution. So what actually we have? As usual, we have Markov chain xi0, xi1, etc. with transition probability matrix pi. Okay, and I call the distribution stationary if just it is preserved by the transition, by the action of the transition probability matrix. So in other words, pi is left eigenvector of the transition probability matrix pi with eigenvalue 1. With eigenvalue 1. So actually, if this transition probability matrix always have eigenvector with eigenvalue 1 or not. In other words, if the transition probability, if it is true that the transition probability matrix always has eigenvalue 1. So the answer is yes, because I can just present you the eigenvector, but the right eigenvector, not the left. Look, because if you take the vector which I denote like that, which is just 1, 1, etc., 1, then I apply to it the transition probability matrix. I should transpose it, right? column vector, then of course I get the same vector. Why? Because when you multiply this matrix by this vector, you just take the sum of elements over a row, right? Просто складываете элементы по строке, but the sum of elements over the row equals to 1. That's why it is true. That's why actually we always have this eigenvalue 1. But of course we always have left eigenvector, because for each eigenvalue you have right eigenvector and left eigenvector. But the problem is that not arbitrary vector can be a distribution, because the vector, what is a distribution? Distribution, it means in particular that all components of the vector are non-negative, right? So pi j are positive, are non-negative for arbitrary j. Also, of course, we should demand that the sum of pi j is 1, but we can always normalize the eigenvector such that it holds. But the problem is that it is not clear at all why such eigenvector exists. If it exists, then it's called stationary distribution. Okay? Actually, it doesn't always exist, and we will discuss it later. Okay, so now let me explain some notation. Let us consider Markov chain. So for the moment we have Markov chain psi0, psi1, etc. And what do we need to fix the Markov chain? Okay, to fix not the Markov chain, but distributions of these random variables. So the initial distribution, as usual, we denote by pi0, the distribution at the moment of time pi1, etc. To fix these distributions, what do we need? We need transition probability matrix, right? And also the distribution pi0. Because once it is fixed, we know to compute pi m. Right? Because the lemma, I do not know, remember the number of this lemma, says that the following holds. Okay? And here from now on I speak only about homogeneous Markov chains. That is, the transition probability matrix does not depend on time. Okay, so now I want to do the following thing. I will preserve the transition probability matrix, but I will change the initial distribution. Смотрите, значит, я буду оставлять ту же самую матрицу переходных вероятностей, но буду менять начальное распределение. And I will call this object, I mean, I will denote this object usually by the same letters, because actually what matters here, the transition probability matrix is important. But the initial distribution, it's natural to change it. So let me write this more accurately. So let us consider the Markov chain. A Markov chain. Consider a Markov chain. Say psi0 tilde, psi1 tilde, psi2 tilde, etc. with the same transition probability matrix pi, and but different initial distribution. Different initial distribution, let me call it, say, pi0 tilde. Pi0 tilde. And let me write down the remark. This remark 16. Often it is convenient to consider Markov chains with the same transition probability matrices, but different initial conditions, initial distributions. I'm using notations. I'm using notation. We will often denote them by the same in the same way. Denote them in the same way. Okay, by the same not in the same way. Maybe it's better to say by the same letter. By the same letter. For example, I mean, if you don't know e.g., it means for example. Okay. For example, as xi0, xi1, etc. So, значит, я просто все марковские цепи, вне зависимости от начального условия, если я зафиксирую матрицу переходных вероятностей, я буду обозначать одинаково. Хорошо? То есть я буду, просто сейчас мне будет удобно менять начальные условия. It will be convenient for me to change the initial conditions. But this is quite natural, because I mean we are talking about some frog which jumps between states with like here probability 1/3, 2/3, and so on, right? So what is important here is these probabilities, but the initial distribution, I mean, you can assume that your frog starts from here almost surely, but you can assume that it starts from here with probability 1/2, and from here with probability 1/2. So I mean, but this is the same frog, right? So it's natural to know these Markov chains by the same letter. Okay, so this. Okay, so according to this remark, let me consider my Markov chain, but with stationary initial condition. So let the initial distribution pi 0 equals to pi, okay? Where pi is stationary distribution. So, but then what we will have? Then Pn equals to what? We know that it equals to P0 transition probability matrix to the power n, right? But what is this? What is this? No. For stationary initial condition. Pi, yes, this is just pi, right? Because the matrix, the transition probability matrix preserves this distribution. It means actually that our frog, which if it starts with the stationary distribution, then it will always live on this stationary distribution. So, если наша лягушка, значит, в начальный момент времени, я знаю, что у нас вероятность всего одна вторая здесь, одна вторая здесь, то через 100 лет будет ровно то же самое. Okay? So this is a very, very natural object. And now let's consider another example, like a physical example, because this is a very physical object. Let us assume that our room is isolated, right? Our room is isolated. So, and let us measure the temperature. The temperature is constant in the room if it is well isolated, right? What is the temperature in the room? The temperature in the room, like the temperature, this is the average, something like average kinetic energy of molecules. Right? The temperature is So it means that the average kinetic energy of molecules is the same for all molecules in our room, and it doesn't change because the room is isolated, right? So actually, what we have, we can represent the movement of molecules as a certain Markov chain. What is the state space of this Markov chain? The state space for this Markov chain is something like r to the power n, where n is a number of molecules. It is huge. It is something like the Avogadro number, right? It is huge, like 10 to the power 23. Actually, it isn't really true because the state space should be this guy squared. Those of you who have already taken the course of Hamiltonian mechanics should understand this, because I mean you should have the phase space. Because the coordinates here, the correct choice of coordinates for molecules are not only their positions, but their positions and their speeds, and you should consider them as independent coordinates. In fact, but this is a Hamiltonian trick.
Why not 6? Why not 6 magnitude?
Right.
Like we have 3 dimensions and
Right.
speed and coordinate.
Okay, 3n times 3n. What I need to say? You're correct. Thank you. 3n times. So these are coordinates and these are speeds, right? So now, okay. This is the same that you suggested. I mean, this state space actually it is not finite. It isn't even countable, right? It's uncountable state space. So that's why our science can be directly applied to the situation. But some similar things can be applied. Actually, the process of movement of molecules can be described by a certain Markov process, not Markov chain, but Markov process with continuous time, with continuous state space. Of course, it's a much more complicated object, but morally it is like the same. So the principal idea is the same, that the future doesn't depend on the past, but depends only on the present. And we can observe similar effects there. In particular, stationary measure also plays a central role in this story. And so returning to the story with the temperature, what does it mean actually that temperature doesn't change? Somehow it means that we are in the stationary state. So when the room is isolated and the temperature is distributed uniformly, we are in the stationary state because the velocities of molecules, the average velocity of molecules doesn't change. In fact, it follows from the fact that we are in the stationary state. But then I open the window, right? I open the window, it's cold outside, and close to the window, the temperature becomes lower than in this corner. Then I close the window, and then I wait during some time. What we will observe? We will observe that the temperature will become again uniform. Of course, it will become lower than before I opened the window, right? but it will become uniform. So we again will arrive to the stationary state. What does it mean? Actually, it means that our process, the distribution of our Markov chain converges when n goes to infinity to the stationary state. And this is a very remarkable fact, which is called ergodic theorem. And in the next lecture, I will prove it in our setting, of course. Actually, for the story about molecules and about the temperature, it is not yet proven. In the sense that, I mean, it is proven if you assume that molecules, the movement of molecules is governed indeed by rather than the degenerate Markov process. If you assume that the movement is just Hamiltonian, as usually people, so at least as people believed in the 20th century and before, then it isn't proven. So now the understanding of such effects is the following. If you do not assume that your mechanical system, like the system of molecules, if you do not assume any stochasticity in your system, for example, you do not assume that in your system you have some random noise or something like that, you cannot prove anything. You cannot prove anything when we are talking about such effects as the effect that the temperature becomes uniform in the room. Once we assume that we have some rather not degenerate random perturbation in our mechanical system, we can prove a lot. Okay, so what people are trying to do, they're trying to reduce this stochasticity to get closer and closer to the real purely mechanical system. Okay. So, okay.
What is the type of convergence that we have?
In our setting, this will be just
Think of room with molecules.
well. This is okay. This is a weak. So, if you are talking about like Markov chains here, it means that we are talking about stochastic differential equations, and this object becomes a measure on this space, and this probability measure. This probability measure weakly converges to another probability measure, which is called stationary distribution. Okay, so here is simple.
So does it work for any distribution P?
The point is that in the next lecture I will prove that under some, of course we need to assume something, right? Under some quite natural assumptions, this holds for any initial conditions, and this measure is independent on the initial conditions.
So no periodic distributions.
Hmm?
So there are no periodic distributions.
Yes, but this I said that we should assume something. If you consider the Markov chain consisting of two states, and with probability 1 you jump from here to here, right? So this isn't true anymore.
Okay.
But this is a bad Markov chain, right? So okay, so this is like the promotion of this story about stationary state. Just to explain, this is a fundamental thing. You can, for the moment, you can forget about this part. I will not erase it, but I will separate it like this. For the moment, let us just discuss the stationary distributions in quite detailed way. Let's consider some example. Actually, okay, yeah. So let us consider the following example. Let us take Markov chain with transition probability matrix of the following form: 1, 0, 1, something simple. Okay? 1/3, 0, 2/3, 0, 1, 0. Have Markov chain with this transition probability matrix, as I explained now.
Sorry.
Yeah.
Oh, it's
Wow, it's stochastic. It's fine. So this is the first state, this is the second state, and this is the third state. So I go from the first to the second with probability 1, from the third also to the second with probability 1, and here I go from the second to the first with probability 1/3, and with probability 2/3 I go from the second to the third, right? So this is very simple Markov chain. Now you see I do not fix initial conditions. I just say Markov chain once I fixed transition probability matrix, as I agreed. Now let me give some simple interpretation of, just to feel it better, of what the stationary measure is and what actually our main formula, this one says. So this is our main formula, right? So main formula, how distribution at the moment of time n becomes distribution at the moment of time n plus 1. So actually what it says, let me write for this particular transition probability matrix this equation in more details. I mean, it's very simple. This is Pn plus 1 first component. This is just the second component over 3, right? P2n plus 1 over 3. P2n plus 1. The second component, this is, okay, let me write first maybe the third component. This is P2n plus 1 times 2 over 3. And the third component, the second component has the following simple form. This is P, the second component, this is P1 plus P2, right?
Sorry, we want to describe Pn plus 1 in terms of Pn, not Pn plus 1. But
Thank
you...
You're right. Thank you. Yes, thank you. Okay, now it's better, right? So I've just written this equation, right? I've just written this equation. So this guy has three components, 1 and 2 and 3n, and I've written this equation explicitly. Okay, so now let me suggest the following like geometrical or physical as you wish interpretation. We have 3 heaps of sand. У нас есть 3 кучи песка. Значит, 3 кучи песка. Каждая куча лежит на своем, так сказать, состоянии. So each heap, one heap is here, the second heap is here, the third heap is here. The sum of sizes of these heaps have exactly these sizes. So these are the mass of the heaps. То есть масса первой кучи, масса второй кучи, масса третьей кучи. The sum of the masses is 1, right? The sum of the masses is 1. And what is the step in the Markov chain? The step, I mean that I pass by my arrows once. I mean that I do this. It is the following. The following thing. I take the heap which is on the second state. I divide it with ratio 1/3 and 2/3. This part is 1/3. I take this part of the heap and I put it to the state 1. To the state 1, right? And this part of the heap I put it to the state 3. The heap which was before this at the state 1, I take all this heap and I put it here, and all the heap which was there I put here. Значит, если я беру вот эту кучу песка, разделяю в отношении 1/3 2 третям и кладу 1/3 сюда, 2/3 сюда. А кучу, которая была здесь, всю кладу сюда. И кучу, которая была здесь, всю кладу сюда. This is exactly corresponds to what is written here. If you think about this P and J is about masses of the heaps, right? And actually, when we want to find stationary distribution, we want to find such distributions of masses of these heaps that after this process, nothing changes. Okay? So I do this process, and I have the same heaps. Just easy to guess this distribution. Просто можно легко догадаться. Just easy to guess. What is this? What is this? Okay, let me copy it. 1/6, 1/2, 1/3. Right? Now let us look if it is okay. Indeed, when I take 1/6 from here and 1 over 3 from here, I add them and I obtain exactly 1/2. When I divide 1/2, 1/3 here and 2/3 here, I obtain exactly 1/6 and 1/3. This is just interpretation to understand what is going on actually. But formally, of course, you can you can, when I ask you to compute the stationary measure, you just solve the equation, just solve this equation and that's it. Right? Just solve this equation. Просто решайте уравнение и все. Actually, if it is true that in this, so in particular it means that for this particular Markov chain the stationary distribution exists. If it is unique for this Markov chain or not. If it is unique.
Yes, we have three equations and three.
Yeah, exactly. Because when I should just rewrite these equations, right? For these equations for the distribution pi. So I'll get pi 1 equal to pi 2 over 3, pi 3 equal to 2 pi 2 over 3, and pi 2 equal to pi 1 plus pi 2, and then you just solve this equation and you find that this is a unique solution. So in particular, stationary distribution is unique in this case, but it isn't clear that it's unique in general, right?
Well, if the determinant of pi isn't equal to 0, is equal to 0, it is obviously not unique.
Yes, but no, it isn't. I mean, it isn't so clear because you want to find not arbitrary solution, right? You need to find only the solution such that pi j is non-negative and sum of pi j's equal to 1. You need only this solution. So it's slightly more delicate. Okay. Okay. Let us go on. So natural question. If it is true that the stationary distribution, okay, when the stationary distribution exists, for this example it exists, it's okay. So if it is true that it exists, it always exists. Particular partial answer is the following. This is theorem 17. Theorem 17. Any Markov chain, of course, homogeneous, right? It doesn't make sense to talk about stationary distribution if your Markov chain is not homogeneous, because your transition probability matrix changes in time. With finite number of states, has a stationary distribution. Stationary distribution. Okay, what is going on with infinite number of states? In your homework, I'll ask you to find an example when Markov chain has infinite number of states and stationary distribution does not exist at all. Значит, для бесконечного числа частиц это не всегда так состояний. I mean, it's very simple. I think that some of you have already found this example. Right? Of course, under certain conditions, this theorem also holds for infinite Markov chains. But I mean, this is more delicate. I will give you two proofs of this theorem. One proof is very short, like 2 lines. Another proof is more complicated, but another proof is very, very general and it's widely used in some more complicated situations. For example, the first proof works only in this setting for finite Markov chains. The second proof will work, for example, for Markov chains on Hilbert spaces, blah blah blah, something like that. So, first, let me before starting the proof, let me introduce some notation. So So I'll denote by such row the state of all distributions, set of all distributions. Okay, let me write it more accurately. So this is a set of all vectors pi of the form p1, p2, p3, etc. Okay, sorry. Let me denote from now on. I will denote by L number of states of my Markov chain. Okay, so I have state 1, etc. The last state is L. Then my distributions have only finite number of components, L. And by this row I will denote the set of all distributions. So this is a set of all vectors from Rl such that their components are non-negative and the sum of their components equals to 1. Equals 1. Okay? So this is the set of all distributions. It's immediate to see that rho is a simplex. It's a simplex, right? The simplex, it means that if you take okay, I mean, so you know what is a simplex, right? So you take number of points and you take their convex half. Okay. This is a simplex in RL. So in particular, rho is a compact set. Is a compact and moreover convex set. Convex set. When I say in RL, like it's natural to think that I'm talking about the Euclidean norm, right? But the choice of the norm is always delicate thing, and for Markov chains, turns out that it's much more convenient to work with the L1 norm. Not with the Euclidean norm, but with the L1 norm. So I will denote for vector V from R to L, I will denote the L1, its L1 norm as follows. The norm is subscript 1. This is just the sum from 1 to L of the absolute values of the coordinates. So this is a standard notation. In this assertion, since all norms in finite dimensional space are equivalent, of course this holds, this assertion about compactness, it holds also for rho provided with the L1 norm, right? With the L1 norm. And from now on, I will think about rho as about compact convex set provided with the L1 norm. So now proof of the theorem. Maybe somebody can suggest the proof. Okay, Okay, so do you have ideas how to establish the theorem?
Maybe a Brouwer theorem.
Exactly. So we have Brouwer fixed point theorem. Fixed point theorem, which affirms that any continuous mapping of a compact convex set to itself has a fixed point. Right? Do you know this theorem? So if not, just read it. I mean, it's simple. So rho, provided is everyone knows this is convex, as we have already discussed, compact, and then I consider the mapping given by the transition probability matrix of the space of all distributions to itself, just acting as just I multiply my distribution from the left. Okay. So the distribution goes to the distribution, sorry, to the right, multiply to the right by the matrix. Right? The distributions I recall that I view them as row vectors. Okay? So this is continuous because just multiplication by finite matrix. So that's it. There exists phi, which is distribution such that phi is a fixed point so okay. This is a proof. Any questions? No questions. Okay, now let us give much more complicated. So what are the problems of the proofs? Of this proof? So problems of this proof. I mean, it strongly uses heavy uses compactness, and it is not constructive. I mean, we have proven only existence. Right? We don't know how to find it. Okay, well, we know just you can solve this equation, but I mean, it isn't clear that it's easy to solve it. If, for example, the size of the matrix is very large, its computation is very complicated, even by computer. So, second proof. The second proof, you will see it also uses some compactness, but not in such heavy way. Because in applications, you just replace this compactness by some strong estimates. One, you have some additional estimates. Maybe I'll even try to give you some exercise to see this. Okay, the second proof, it also uses compactness, but you can replace it by some estimates, some a priori estimates which you may have in applications. So second proof, it's called Bogolyubov-Krylov method. It's indeed very widely used. That's why I want to give it also in these lectures. So let us fix just arbitrary initial distribution. Just arbitrary. So this will be the starting point somehow. Then what I will do next? I will consider the following object, which I will call phi k. This is the sum from 1 to, say, k minus 1, or from 0, maybe I write down not I, but n, 1 over k of p n, where p n, these are just distributions which are obtained from the initial distribution along my Markov chain. In other words, in such a way. Right? So I start with arbitrary initial distribution. I compute the distributions till time n, and I average them. Okay? And I call this guy pi k. Then look, this pi k, they all belong to rho. This set is bounded. They belong to rho. Do you see this? Right? Because pi k j, each component of this vector, these are vectors. Right? These are vectors. So all components of these vectors are non-negative, because all components of these vectors are non-negative. And moreover, sums of their components are they equal to what? They equal to 1 over k sum from n 0 to k minus 1, sum over all components of these vectors. I have just exchanged the two sums. But this equal to what? The distributions, right? Then to 1. So here I have k, I divide over k, I obtain 1. Equals 1. So these guys indeed are distributions. In particular, they are bounded. This sequence is bounded. Okay, so it isn't needed, because look, the set rho is compact. It's compact, right? It's compact. Then there exists a sequence, subsequence kj, such that the subsequence of these distributions by kj converges. In rho with the L1 model. I mean, okay, it isn't important with which I will even erase this, because if it converges with one norm, it converges with another, because all norms in finite dimension space are equivalent. Hey, I agree. This is the place where I'm using compactness. But in fact, here I do not need this compactness. I need only that this sequence is bounded, because we know that in RL, the bounded sequence have convergent subsequence. I mean, in more complicated situations, like in infinite dimensional space, you will need some stronger estimates. Which show that in fact this sequence belongs to some compact subspace, but I mean it's doable. Okay, it converges in row. So let us denote the limit of this sequence, of this subsequence, by pi. And I think that you have already understood that this pi will be the stationary measure. So I claim that, значит, я сейчас покажу, that pi is a stationary distribution. So it is clear that this distribution, because my sequence converges in a row, right? In a row. So all elements of row is just distribution. So it remains to check that it is stationary. How to check it? No, I just need to apply the my transition probability matrix, and to see that nothing changes. To see that I will get the same distribution. What is this? Actually, pi, it is limit of these guys. Okay, let me write it in quite detailed way. Here it is pi kj. But look, multiplication by the matrix is continuous operation, right? So I can put it inside of the limit. Okay. Then I'll just write the definition of this guy. Who is this? Okay, maybe I will just write this guy separately without writing the limit. It will be shorter. So this is a 1 over kj, sum from n equal to 0 to kj minus 1. This is just the definition of pkj. pn, right? And I should apply the matrix. P, also I can put it inside of the sum, so I write it like that. Then, what is this? This is just Pn plus 1. So I can write it just changing the limits of the sum. So now I should take this sum not from 0 but from 1, because of this plus 1. Okay, let me write it more accurately. From 1 and 2 kj, and here instead of writing pn plus 1, I'm writing just pn. Okay, but look, this is almost the same that pi kj. Pi kj, this is the sum from 0 to kj minus 1. Here.
The upper limit of the sum must be j minus j.
The upper.
Yes.
No, kj minus 1, because this was the definition of. You showed till k minus 1. Okay? The definition.
Kj is an index in a sequence of pi's. Yes.
Kj. This is.
Okay. Okay.
It's okay.
Yes.
Okay, so look, this sum is almost the same as this sum, as the sum in this definition of pi kj. What is actually the difference? The difference in the first and the last term, right? Only two terms in the sum of k. Okay, kj. But then you divide over kj. You divide over a large number. So these two guys, they will just die under this division and under the limit. So look, now I write it down. I want to say the following thing. I say that this just equals to pi kj. I should subtract the first term of this guy, because here I start from 1, not from 0. So I should subtract pi 0. Okay, let me write it like that. Subtract pi 0 and add the last term, because here I should sum till kj minus 1, and here I sum up till kj, right? So plus kj. Whoa. Okay. These were the brackets. It doesn't work. Okay, so here I should have a bracket, but I cannot draw it. I might pretend like that. Yeah. So then I will draw this bracket. Okay. But then, when kj goes to, when j goes to infinity, this guy, by the definition of pi, it converges to pi. But this guy, look, they are bounded. They are bounded.
Why is there bounded?
Because they belong to rho. They belong to rho. What is a norm? Norm, for example, of pi, L1 norm of this guy. What is this? This is just sum of its components because they are non-negative. It is 1. Right? It is 1. And similarly for this guy. By the triangle inequality, their L1 norm of this sum is less or equal than 2. Okay? So it means that this bracket, all this bracket, it goes to 0 when j goes to infinity. J goes to infinity. So we get that pi is stationary. And this is constructive. So again, what you are doing, this is very, very, very famous trick which often works. So you take arbitrary initial condition, just arbitrary. Arbitrary initial condition. Then you take your trajectory till the time n, and you average out along this trajectory. And then turns out that this sequence have convergent subsequence, and this, if it is so, then the limit always will be the stationary measure. In our setting, it indeed has the convergent subsequence because of the compactness. If you don't have compactness, you need to work more. You need to prove some estimates and to get some. Finally, you always get some compactness if this result is just true and if this method works. But it works, I mean, almost always. Okay, questions? Questions? What? See. Okay, you have another 15 minutes, right? Very good. No questions. Perfect. Let me write down the following trivial corollary, but I think it's quite nice. Corollary 18. Any stochastic matrix has left eigenvector with eigenvalue 1. Okay, not with, corresponding to. Corresponding to eigenvalue 1. With non-negative components. This like nice corollary for linear algebra. Just take Markov chain with this with transition probability matrix given by this stochastic matrix. This Markov chain has stationary state, right? This Markov chain has stationary state, and this stationary state. This is exactly left eigenvector corresponding to eigenvalue 1, and these components are non-negative. That's it.
In the definition
Fine.
of the stochastic matrix, do we have the finite requirement for stochastic matrix to be
For
finite?
what we have been doing before, not, but not now she required, of course. Yes. I don't think there is a classical definition in the sense that you can naturally speak about infinite matrices and also call them stochastic. Here, of course, we need to ask the matrix to define it, otherwise it doesn't work. Okay, so the next. So now we know that for any finite Markov chain stationary state exists, and we can finite. I mean, with finite number of states. And now we can discuss the conversions to the stationary states. This is what I've announced in the beginning of the lecture. Today I'm going to formulate the theorem, but at least I'm sure in that. But at least I will formulate some preliminary definitions. So this part will be called ergodic theorem. And this is indeed the main theorem of the course. Ergodic theorem. Definition. A transition probability matrix. Transition probability matrix pi is called mixing, перемешивающая. Mixing. I'll write it also in Russian. Перемешивающая. Эргодик, понятно, эргодический, значит, а перемешивающий это менее понятно. Перемешивающая, да, длиннее получается. It's called mixing. If there is natural number S such that you take your matrix to this power S, then you take arbitrary components of this matrix and you get positive number, strictly positive. So there exists power of this matrix such that the resulting matrix is non-negative. So strictly positive. All its components should be strictly positive. Okay? Okay. Let us first discuss the definition. I mean, going ahead, the formulation of the ergodic theorem will be as follows: if the transition probability matrix is ergodic, then this convergence to the stationary state holds. Moreover, with exponential rate. But that's why this definition is so important. So now let us before formulating the theorem just discuss this definition.
Sorry.
Yeah.
You mentioned ergodic matrices. Is it the same?
Ergodic matrices. Okay. Yes. This is mixing matrix. Yeah. Yes. This is the same. Sorry, because I mean the problem is that here there is no canonical terminology. In many textbooks, these matrices are called ergodic. But now there are too many ergodic, like word ergodic appears just everywhere. You have ergodic Markov chains, which can be ergodic even if the transition probability matrix is not ergodic, and this explodes the mind. So we just change the terminology. I will discuss the terminology later on, but just once you take a textbook, it isn't clear what they call ergodic. You just should check every time. Examples. Okay. Sorry. No. Before examples, I should make the following comment. So actually, what is this guy? We have already seen this object, and we denoted it in such a way. This is just according to I will written down the number of corollary. So who is this? This is the transition probability in time s. So when you
No.
yes.
It's a probability that in time s we are placed.
So this is I mean according to corollary 12, this transition probability in time s. What do I mean? I mean the following. If you remember, once we considered a Markov chain not in one step, right? But in I think I used letter n in n steps. But now it is not n anymore, it is s. In s steps. Right. So we are interested what is going on if I make not only one step, but I make s steps. And we proved that the resulting process is also a Markov chain. And we found its transition probability matrix. This transition probability matrix is obtained just by taking the transition probability, the original transition probability matrix, to the power s. Okay? And that's why the elements of this matrix, we call them transition probabilities in time s. Okay? And denoted in such a way. So actually, what does it mean? What does it mean? It means that matrix, transition probability matrix, is mixing if there is a time s such that exactly in time s, so exactly in time s, you can go from arbitrary state to arbitrary. You can not go, you can arrive. You can arrive from two arbitrary state, starting at arbitrary state. То есть, значит, мы можем из любого положения ровно за время s попасть в другое. Вот что нам нужно. Потому что такое, значит, должно быть такой момент времени, что переходные вероятности вот ровно за это время все положительные. То есть, значит, за время s мы можем попасть из любого положения в любое, ровно за время s. Okay? So I just repeat something in Russian. Yeah. So I say nothing new. Okay, so in particular, what does it mean? Let us consider an example. I mean, I think it will be I think simpler to look at the example. For example, we have such Markov chain. I mean, such transition probability matrix: 1/2, 1/4, 1 0 0 0 1 0. Okay, so let us draw the graph of this matrix. So actually, I mean, it isn't very pleasant to try to understand if this transition probability matrix is mixing or not, because I should take square of this matrix and third power and so on. It is computational not so easy. So, but instead, let us just draw the graph of this matrix. So here I have state 1, state 2, state 3. So I have narrow like that. Here I have. I even will not draw. I even will not write down the probabilities above the arrows. I will only write down the arrows. So if the probability is positive, I write down the arrow, right? So I can go from the first to itself, from the first to the second, from the first to the third. Then I can go from the second to the first, from the second to the first, and from the third to the second. And then let us look. If it is true that this matrix to the power 1 is positive, no, because we have zeros, right? And we see this on the graph. I can iterate from state 3 to state 3 in time 1. Okay, if it is true that this matrix squared is positive, just no, because if it is, then I could arrive from the state number 3 to the state number 3 in 2 steps. Если бы эта матрица в квадрате была положительной, все компоненты были положительные, значит, что все переходные вероятности за время 2 положительные. Да? Значит, я могу из состояния 3 прийти в состояние 3 за 2 шага. Но я не могу, потому что раз и 2. Все, других нет. Да? So, no, it isn't positive, because from the state 3 I go here, and then I can go over here. I cannot write from the state 3 to the state 3 in time 2. So, no, this is false. But if it is true that the matrix the power 3 is positive, look, from the state 3 to the state 3 I can arrive in 3 steps, 1, 2, 3. From the state 1 to the state 1 I can just 1, 2, 3. From the state 2 to itself, 1, like 2, 3. Okay, from the state 1 to the state 2, no problem, 1, 2, 3, and so on. You see them from the state 2 to the state 1 in 3 steps, 1, 2, 3, and from the state 1 to the state 3 I can, okay, this you see this, how it is called? Yeah, this loop, thank you. This loop is very convenient because I can make here a number of passages I want. So I can stay here so long as I want, as long as I want. So I can pass. So it's easy to check in such a way that I can pass from any state to any state in 3 steps. So it means that this matrix is positive. Yes. So actually it means that in order that the property of the matrix to be ergodic, I mean to be mixing, it is to say if the matrix is mixing or not, we do not need to know these numbers. We need to know only if they are positive or not, right? That's it. So to see if the matrix, the transition probability matrix is mixing or not, we need to know only the structure of the graph. Not the probabilities, the transition probabilities. Not the transition probabilities. Okay. Just to finish with, I will give an example of transition probability matrix, which is not algorithmic. Maybe you can suggest such an example. Actually, you have already seen this example today.
Oh yes, something with sand, because we, I don't know.
Something with sand you can have everywhere, just to take sand.
Yeah. Diagonal matrix. Diagonal matrix.
Diagonal matrix. But I mean, it's boring. Could you suggest? I mean, this Markov chain is not even connected, right? But formally you're right. But could you give an example of a connected Markov chain, but which is not algorithmic?
Проблема.
Hmm?
Нужно это просто.
Что?
Ну, если с четностью сделать проблему.
Да.
то
So you see, this I mean, I even wouldn't say that this is a Markov chain because you do not have any stochasticity here. You always go with probability 1. You just make a flip, right? You make deterministic flip. But this is not algorithmic. This is not algorithmic, of course, because just I mean it's clear that when you take this matrix because you can go from 1 to 1 only in pair number of steps, and from 1 to 2 only in odd number of steps. Sorry, pair is in French, in even number of steps. Okay. You see? So not all matrices is very great. So the next time I will convey it all. The next time I will prove the algorithmic theorem. Maybe I will discuss something more. Then the next time this is the next time it is, I mean, this is the week for exams. Yeah, but this is the last day of exams, and so I will make the lecture. Sorry, but anyway, it's recorded. The problem is that maybe this is the most important lecture in the course, but well, just the time is so limited, so
I have a question.
Yeah.
On 4th of November, it's
this
holiday.
is a holiday. I think that was the day I made something. So I was saying
It wasn't.
I wouldn't like to just to skip this day completely. Maybe I'll make something like discussion of problems. I'll just record something like that. See? Yeah, because concerning the problem, so we'll have control work as I've announced on 11th, yes. And control work as I've announced, it's impossible to retake it. Principally, just because this work will mostly consist of problems that I was given during after the lectures, which are all on the website, and you can always solve them, and you can always ask me questions if my solution is correct, if I don't understand how to solve, could you give me an advice, and so on and so forth. Moreover, I think that maybe after the next time I will ask you to choose like 3 problems which I will write, or I will write them down, the solutions. Not. I mean, we have some elections for these problems, not the problems from each person. So But it doesn't mean that you can ask me about other problems. You can ask me about any problem. So I hope that you solve this problem because otherwise the lecture will become much less interesting. Но там есть какие-то совсем тривиальные задачи, на которые нужно подумать, ничего подобного мы не обсуждали этим задачам. Поэтому, наверное, на вашем месте займемся этим заранее. Взял условия учился, взял условия учился,